Check it out now, y'all.
nanoHUB-U, online instruction.
All right, welcome back. This is week 2 of the course Thermal Energy at the Nanoscale. I'm Tim Fisher from Purdue. And this week we're going to talk about statistics and generally focus our attention on thermal energy carriers, but we're going to have to start with a little bit of background. And so I will forewarn you that it'll seem a little bit confusing, maybe a little bit dry at first, and hopefully by the end at least we'll get to some transport problems this week. We have to build from the base, and so we're going to talk today about statistical ensembles. We'll motivate it with the following thoughts. First of all, people certainly talk about nanotechnology an awful lot these days. And when people ask me what I think about what is nanotechnology, I don't usually think about a particular length scale, but I generally think about some kind of attribute where an effect that becomes prominent at small scales or sub-continuum scales can somehow be directed toward a purpose, a technological purpose, therefore the word technology inside of nanotechnology. So why do we care about statistical mechanics? Well, really nanotechnology doesn't work. I don't know of any nanotechnologies per se where just one nano object does everything. And so what we really want to do is to create some useful macroscopic effect, at least something that we can read or measure on the basis of this sub-continuum phenomenon. And so to do that, most of the time we have to have a lot of nano things working together. And that means that we're looking at really the collective behavior of nanoscopic entities. And to do that, if we want to take advantage of that, we really need to know how those nanoscopic entities, those collections of entities, in other words, ensembles, how they work together, how energy is distributed amongst them, and so forth. So that's why we're going to spend some time on statistical mechanics. Now, statistical ensembles are somewhat confusing to people the first time that they see them. I want to think about a collection of objects, and we're going to have certain attributes of those objects. First of all, we'll have a number of particles that'll be capital N, and I know that we use capital N in a couple of other different contexts in the course. I usually try to put a subscript on things to distinguish them from other similar entities or other things that we use capital N for. But here, in the statistical context, that's the number of particles in our ensemble. We could also have volume, how much space these N particles occupy, and energy. Those will be the big three for us for this part. Now we'll think about this collection of particles, and it can exist in a variety of different states. And in each of those states, those variables could change. I could have more or less number of particles. I could have a larger or smaller volume, or more or less energy. And so we'll have to now look at not just the number of particles, or not just the volume, but how they all work together. And each of those each collection of N, V, and E will become a state. Okay? Now, there's a fundamental premise for statistics, at least for statistical mechanics, and that is if we were to measure something, for example, if we wanted to measure temperature, we would assume, or the statistical assumption is, that all of these allowable states they occur during this measurement, so that what we actually observe is an average of all the possible states. Now that average could be weighted toward one or the other state, but generally speaking, we're sampling all of the possible states. So that's an important premise as we move forward. We'll start out with the simplest ensemble. That's called the Microcanonical Ensemble. And we'll focus on something where we have a determined number of particles, a determined volume, and an energy at least between a level E and some increment above that. So E plus dE. This is a little trick that you'll see often in differential physics. We will denote this number of possible states with that collection of attributes, n, v, and e, as omega. And we'll put the subscript nu on that. And so a lot of times it's hard to distinguish nu from v, and depending on what font you use. But when I say nu, at least the symbol nu, that's what I'm talking about. Again, that statistical assumption comes into play. And so if all of the states are equally probable, that's at least our first order approximation, then the probability that this state nu exists, that's the collection n, v, and e, is simply the inverse of omega, or this number of states or density of states. It's a little bit different than the kinds of densities of states that we'll talk about in just a couple of lectures from now. Now, when we fix n, v, and e, that's what's called the microcanonical ensemble. And when we by fixing it, we can study a lot of the statistics easier than we can when we allow something to vary. So that's why we start out with this simplest ensemble. Now, entropy is another important thermodynamic property, also a confusing one. Certainly I was confused when I first learned about entropy, and often I still am, but I have at least it figured out a little bit. The second law of thermodynamics is the driving force behind entropy, in the sense that the reason that we need it is that we need to understand entropy is that we have the second law of thermodynamics. So entropy is the variable through which we kind of interpret the second law of thermodynamics. And what the second law really states, and there are many different ways to state the second law of thermodynamics, but in essence it means that the disorder of a system will be maximized. It will always tend toward being maximized, at least if left on its own. So that maximization of randomness or disorder can be captured in this idea of entropy. So we want entropy, according to statistical convention, is proportional to the logarithm of omega. So omega, again, was that number of states or density of states. So if I have more possible states, my system will be more disordered, right? And so entropy would increase. And the constant of proportionality is Boltzmann's constant. Now, entropy allows us, through classical thermodynamics, to give a definition of temperature. It's not the only definition of temperature that you could have, but it will be our definition of temperature for the purposes of this course. And so temperature, the inverse of temperature, is actually the derivative of entropy with respect to energy, while fixing the number of particles in my ensemble and the volume. There's another factor that shows up a lot. We'll use it a little bit, not too much, but we will use it a little bit and go back and forth. This term beta is the inverse of thermal energy. And so by the definitions that we've just described, if we substitute our expression for entropy into our expression for the inverse of temperature, you can see that leads us to this beta, or inverse of thermal energy. And that, in turn, is related to the logarithm of the number of states. And in fact, it's derivative with respect to energy. So if we move up to a slightly higher level of complexity, if we wanted to relax one of the constraints, the one that I'd like to relax first, and I think most of the time this is what folks do when they're studying statistics, is to relax the energy constraint. So we now want to let our energy float, okay? And we'll do that in a somewhat odd way, I suppose you could say, in that we still want to take advantage of the nice the simplicity of that microcanonical ensemble when everything was fixed. And so what we'll do is we'll take a microcanonical ensemble. So that's shown down here. That's the system that I've drawn. That's the large, or the small rather. That's the small box or rectangle here. plus the bath around it. And we'll say that together they will have fixed number, volume, and energy. And we'll actually, inside of this system, that's going to be our focus, we'll say that the number and the volume also will be fixed, but we'll let energy flow back and forth between the bath and the system. We just won't let it go outside of the bath wall. And so this is called the canonical system. That would be just this system down here. And when we group it together with the bath, then it becomes a microcanonical ensemble, and then we can use some of the principles that we just covered about the probabilities. So the first law of thermodynamics, I think it's intuitive and also familiar, I hope. That is that the total energy of my bath plus my system has to be conserved, and so it's just the sum of those two energies will equal what we'll call capital E. Same thing that we called it before. That's the energy in the microcanonical ensemble. Now we're going to consider the system in one definite state. And again, we're going to use this term nu, again with a slightly different font, but this is the term nu that will represent one state in our system. So that's number n, volume v, and energy E. The number of possible bath states, if we just use the first law of thermodynamics, remember that that we had the density of states omega was going to give us was related to energy primarily, right? And so now we're looking at the number of possible bath states, and that will be related through the first law of thermodynamics. We can substitute the total energy minus the system energy. That's E sub nu. Now we have to make an assumption here. We expect that the probability of our system state will be proportional to the number of corresponding bath states. That would kind of make this make the system energy plus the bath energy equal our total energy E, which again is not changing. And so we make that approximation. We say that the probability of this state will be proportional to, again, that's the number of bath states, which we just covered above, and we're representing it not in terms of the bath energy, but rather in terms of the difference between the total energy of the system and bath and minus the system energy. And then we're going to do something that looks a little bit odd. Instead of just expressing this direct proportionality, we're going to call omega of E minus E nu, we'll call that E to the power of the logarithm of omega E minus E nu. This is just a simple mathematical identity, but what it allows us to do, remember we had a relationship between the log of omega and entropy from before. What we'll do is we'll actually do a Taylor expansion. We'll assume that our system energy is much smaller than the total energy, right? And that's reasonable, both because we could make our system very small, and also we're only looking at one state, and we're fixing that state, one definite state inside the system. When we do that and apply a Taylor expansion of this logarithm, that's shown here, right? So we can now express our logarithm in terms of the log of omega of the total system plus bath, and that helps. We've seen that a little bit before. And again, a derivative term. So this is the derivative of the log of omega with respect to energy. Well, we've seen that also. That was actually beta, or the inverse of thermal energy, from just a few slides ago. So now when we substitute, we kind of combine these different concepts that we've just covered in the bottom half of this slide together. We find that we can express our probability that a state nu is occupied is proportional to E to the minus beta times the energy of that state. And that is very powerful. It actually, probably looks familiar, at least to some of you. We tend to see these probabilities in exponential terms in our distribution functions, in our statistical distribution functions, especially as applied to solid state principles. So we now have to normalize that. So the sum of these probabilities has to be equal to 1, right? Otherwise, we would have too few states allowed or too many. So they all have to sum up to a probability of 1. And so what we'll do is we will define a partition function. This partition function is called Q in most texts. This is again for the canonical ensemble. And so all we do, that partition function is out there. The only thing it does is it makes sure that when we add up all of these probabilities, they equal 1. Once we have that, then we'll say that we can calculate averages. And the way to calculate averages in a statistical manner is to what I call apply moments. So if I wanted to calculate the average energy, that would simply be what I call the energy moment of the probability, meaning a moment meaning I'm multiplying by something. So I'm multiplying the probability of each state by energy, and then I'm summing over those probabilities. When we do the simple substitutions of these various factors here, you can see that proceeding inward or proceeding through this process, we find that we can express, again, there's the partition function in the denominator. Again, we have our energy of our state, E sub nu, multiplied by, this is our probability for each state. It turns out that we can express this Q in terms of beta, right? And in fact, this term here collectively is simply the derivative of our partition function with respect to beta. All right, so that's simple mathematical identity. It may not be obvious. It may not even be obvious why we're doing it that way. Again, there's a negative sign in front that comes from the factor and the exponent. But the point is, and really the reason we're doing this is that brings us actually back to another derivative of a logarithm of a function. In this case, we call it the partition function. And so now we're relating energy back to our partition function, which in turn was related to these probabilities. It's actually the normalizing factor for the probabilities. The nice thing about doing it this way is that we can express averages in terms of some of these statistical quantities and these probabilities that it's not particularly obvious. And again, in this case, we're differentiating with respect to beta. That's that inverse of thermal energy. Now, we'd like to be even more general than what we've been so far. And for those who've studied thermodynamics in the past, you will recognize the first bullet. In general, and there are some exceptions to this, but in general, the thermodynamic state of a system depends on two independent thermodynamic properties. So that if I know two independent thermodynamic properties, I can find all of the other ones, okay? And that's at least for simple systems, simple compressible systems. But it serves the purposes here. So we're going to make it a little bit more general at this point, a little bit more abstract, and then we'll bring it back to some very specific examples today and through other lectures. So let's say I was interested in 3 thermodynamic variables. Let's say that they're S, entropy, E, energy, and some other one. We'll call it X. It could be the number of particles, for example. And so then we can form, this is one of the Maxwell relations, we can form a relationship among them so that if I knew X and E and their mathematical functional forms, I could then calculate S, or some change in S based on a change in energy and a change in the variable X. So now if we let E and X vary, and we would maybe have to fix another variable. We would call it generically Y, but it could be, Y could stand for the volume, for example. That's our three thermodynamic variables that we started with were N, V, and E, so number, volume, and energy. So if we had that, the analysis is a little bit more complicated, but the result is not too much more complicated. We end up showing that we could do, in essence, the same kind of probability analysis that we did before, and instead of just having a beta E term in the exponential, now we would have this xi x term, which comes from up above. It's the extra variable that we're adding, because we're allowing that to vary. in that case, we would also need to define a new partition function. So that's xi here. That's capital Xi. And so this is defined just like the partition function was before, but we have to add this extra term. And then the nice thing about this is once we have the partition function defined, the average energy takes essentially the same form that we had before. It's the derivative of the log of the partition function with respect to beta. That's the inverse thermal energy multiplied by -1. And really for any variable we could do the same kind of thing. All we need to do is to find out what variable goes with x. So this is xi goes with x back in our classical thermodynamic equation, and we take that derivative of the partition function with respect to that variable, and we can find an average of the variable x. So it's all pretty clean, and this is why the partition function is such a powerful concept, is that it kind of captures all of these statistics, and if you know the partition function or can calculate it, then you can calculate averages. And again, getting back to what we started with in this lecture, we really want to calculate kind of effective properties of large ensembles of things for some useful purpose. So in the grand canonical ensemble, we're going to make it a little bit specific, so that variable x is now n, and the variable lowercase xi, that's mu, and mu might be familiar, especially to the electrical engineers. That'll be the chemical potential of the system. So now let's imagine that we have a state that has n1 particles. They each have E1 energy, and then we could have n2 particles with a different energy, and so on. What we'd want to do is to average over these particles, the average number of particles, the average energies of the ensembles collectively, of the individual states, and so on and so forth. Well, we have to do one more thing before we get there. We start out with this restriction on the number of particles. So different kinds of carriers have different kinds of restrictions on the number of particles. So here, capital N could be any integer value, and we call these Bose-Einstein statistics. So these kind of statistics allow for integer occupation numbers. We've already touched on Bose-Einstein statistics a little bit, at least we've used it. Then the other really important kind of statistics comes from carriers where the number n in a given energy state E is very much restricted to either 0 or 1. And I hope it doesn't surprise you too much that those carriers are electrons, because the Pauli exclusion principle keeps the occupation at 0 or 1. And then there's another quantum number for spin, so that we could actually have 2, right, up and down spin in one of these energy states. We'll add that factor of 2 a little bit later when we need it for analysis. So again, a little bit back to the nomenclature. One of the challenges in offering a course like this, it's really any course in solid state physics or that has to do with solid state physics, is that the nomenclature in the literature is quite varied. So I'm going to try to stick to some things. We kind of started with N because we wanted it to be intuitive, so N stands for number. But as soon as we take the average number N in a given state, we're going to call that F. Now, you say, why would that be? Well, the answer is this is our distribution function. We've used it already before. And so this distribution function, F, is the average of N. And we'll use F's almost exclusively from now on. Just a little bit, some other examples where we'll use N if we go back. But generally speaking, for these occupation numbers or distribution functions, those are the same thing. They're synonyms, at least in the context of this course. Those will be our distribution functions or occupation numbers. And it turns out that almost regardless of what kind of statistics we have, the form of the distribution function or occupation number, average occupation number, is very similar regardless of the kind of carriers we have. So Fermi-Dirac statistics would have the form like this, except gamma, the last term, is equal to a positive 1. Whereas Bose-Einstein statistics tell us that gamma has to be minus 1. That's the only difference between the two. And then there's one other kind of statistic that is important, certainly especially for gas dynamics. And that's Maxwell-Boltzmann statistics, where gamma is 0. And Maxwell-Boltzmann statistics tend to be actually the other two, Fermi-Dirac and Bose-Einstein, actually tend toward the Maxwell-Boltzmann distribution for cases where the numerator here, E minus mu, is very large compared to the thermal energy KT. You can see that if this whole term in the denominator is very large, it almost doesn't matter what gamma is. The occupation number, the average occupation number, will be just about the same. So Maxwell-Boltzmann statistics tend to apply for cases where you have energy levels that are considerably higher than the thermal energy. So we look at phonons. We're going to go back to phonons here. Now, in the classical sense, if we were to use classical statistics, we would find that the average energy of an ensemble of carriers goes as Boltzmann's constant times temperature. And we'll probably have that as a simple exercise for you to prove. That actually comes from the equipartition principle. So if we actually took the classical harmonic oscillator problem, the average energy of any frequency would be kB times T. And the reason for that, or the part of this that comes from equipartition, is that if I average over time, then I have 1/2 kBT comes from the average kinetic energy, and another 1/2 kBT comes from the average potential energy, which would be stored in the spring of this classical harmonic oscillator. For the quantum case, and we've touched on this a little bit, in that case what we do is we multiply the quantum energy, that's h bar omega, times the distribution function, or average occupation number, that's what I'm hovering over here now, plus a factor of 1/2. And that factor of 1/2 is unexpected, and we haven't derived it, but there are some good references for people interested in this. This is actually called the 0-point energy. So this comes from when temperature goes to 0, we have, that's a term where energy doesn't completely go to 0. There can be actually some finite energy. It's actually 1/2 times h bar omega, where even at absolute 0. So if I put absolute 0 into this exponential term, then the exponent goes to, or the exponential term goes to infinity, and I have an inverse here, right? So that means that that the exponential, that this entire term would be 0. And if I didn't have the 0-point energy, then the average energy would be 0. Okay. Now, the other factor in here that I want to highlight is that when the phonon frequency is 10 to the 13th radians per second, so that's 10 terahertz, when that happens, then the quantum average energy is very close to the classical energy by the time we reach about 100 or 150 degrees Kelvin. And we'll see when we go back and study phonons in real materials, that's a level of frequency that is fairly common. However, when we have higher energy, higher frequency phonons, so 10 to the 14th, so I've just increased the frequency by an order of magnitude here, you'll see that the deviation between the quantum energy and the classical energy, which is the blue line, is quite large, even up to room temperature. These two things would not converge until we had a significantly higher temperature. So with that, I hope that you've been able to pay attention. There'll be a quiz on this, and so hopefully it will help to clarify some things. I just wanted to give you a foundation for some of the statistics that we have, and especially these distribution functions as we move forward. Thank you very much.